Welcome to a brand new episode of Machine Learning Made Simple. Here we unravel the enchantment behind machine learning, demystifying all the technical jargon. I'm your host, Shogato, and I'm here to chat with you about the revolutionary changes unfolding right before our eyes in the tech world. Let's dive in. Welcome to another episode of Machine Learning Made Simple. In today's episode, we'll discuss the recent innovations in the field of large language models. In the past few episodes, we have been methodically discussing the DeepSeek models, their new innovations, and the new techniques that were employed. Now we shift our focus back into the innovations that are happening in the world of machine learning and large language models. In fact, in the last 2 months since the publication of the DeepSeek models, there was a flurry of new innovations. In fact, it's quite common in the research community. Most people either published just before Christmas, or all the papers that didn't get published before Christmas stay in a backlog and get published in the months of January and February. So we usually see a flurry of research papers published during the months of January and February in most of the fields. And the computer science is no exception, and we are seeing massive amounts of research that being published in the months of January and February, and there are a few standouts and major implementations, major innovations that are coming out. One of the papers that came out in very close succession to the DeepSeek models is this simple time test scaling, where these researchers just use a very fine variation, very innovative variation of supervised fine-tuning to fine-tune the output responses and the chain of thought responses to fine-tune back the model to deliver almost equal accuracy as the DeepSeek reasoning models. And we're going to talk about that. And then there are new paradigms that came out which reintroduce our concept called mixture of agents. Remember, we talked about mixture of experts. Mixture of experts is essentially taking different large language models and slicing and dicing their input and output layers and combining them into a mixture of expert model, where the same code gets routed to different experts, and then all those outputs are aggregated for a final answer. And then the final answer is essentially the top voted response. Now, mixture of agents is slightly different. Now, this layer by layer fusion of the large language model is not only just time consuming and extremely laborious process, also offloads those training or those power consumption during the training time to inferencing time. So people with smaller VRAM at their disposal, they are really not be able to take advantage of this mixture of experts, because they just take a large amount of memory and also consume tremendous quantity of power during inferencing time. So these mixture of experts are usually not accessible to consumers. So there is a better way. The better way is the mixture of agents. So you do not merge those large language models, but you run them in an agentic fashion, where the outputs are voted, sorted, and mixed, just like an agentic fashion would do, where you pick the top n responses. So that's essentially the mixture of agents, and we're going to talk about that. So we'll start with the very basic structure of a mixture of agent, and there's this new paper from the Princeton Research Group which talks about the mixture of agents, but instead of using multiple large language models, they're going to use a single large language model. They're very innovative thought process, and what goes into it, we'll discuss all that. Another new paradigm that totally is changing the way we view, and I think this would be one of the seminal paradigms, like the chain of thought paradigm, is a chain of associated thought framework, which takes the chain of thought framework and moves it a little bit in the direction of association, forming word association using Monte Carlo tree search. So that's a little bit more technical or more involved, but we're not going to go into the technical. We're just going to expose the way that they implement the algorithm, so that anyone who is interested can implement that very simply. So we will discuss all of that. Then we have this another new paradigm called Send Retriever, which is similar to the React and Rethink and those kind of frameworks, where the output of the LLM is fed back and the LLM is asked to ponder over it, just like chain of thought and reasoning process, and it's fed back into the large language model, where the LLM performs multiple steps of re-verifications of its own responses. In fact, you probably remember we talked about there are different paradigms which are very similar to this, like self-refine. You take the prompt, you get the output, and then feed it back and ask it to refine it. Self-verification is one. React framework is a slight variation on that. So there are different frameworks which exist where you take the output of the LLM responses, feed it back and ask it to evaluate and perform chain of thought reasoning, and then feed back the output to itself and then ask it to self-verify and perform. So this is a similar, but it takes a slightly different approach where it trains a small model as a thin layer on top of the large language model itself. So you're not actually training the large language model or the fine-tuning the large language model or performing prompt engineering like self-refine or react. So essentially this is somewhere between prompt engineering and full supervised fine-tuning of the large language model. It stays somewhere between because you take any random LLM, it can be even closed source LLMs, and that's the beauty of it. And you can take the output of that, distill the knowledge, and feed it back through that model, and which will perform that self-verification process using some form of reinforcement learning, and then gives you a supervised model, or technically supervised model, which takes the LLM output and performs some form of iterative loop with some kind of a reward function that it learns from the previous experiences, which helps continuously improve the LLM responses. So all the reasoning steps that you see that DeepSeek performs, think of this as on steroids. So it essentially, all these new proposals from the S1 time scaling where they use some kind of a forced budgeting to this Centriver, all of these are taking those DeepSeek proposed reasoning thinking output process and the chain of thought process that they show and putting that on steroids. So S1 did a different approach where they perform a supervised fine-tuning using those chain of thought. This Centriver has actually ended up doing a reinforcement learning based fine-tuning of a model itself, which sits as a thin layer on top of the large language model. And we're going to talk about all that today. And there are many more innovations, and one will be amiss if we didn't mention a few more innovations. Like, while all of these things are going on in the large language model space, because that space is moving at breathtaking speed, image generation models are also progressing at an amazing speed. In fact, if you go back to last summer of 2024, not even 6 or 8 months ago, text to image generation, text to video generation models were like garbage. Like, even the top of the line commercial models, they like produce like 5 or 6 seconds of video. Now we can have a prompt following and prompt aligned video generation from just simple text or audio, which would look almost realistic. And there is substantial progress in this, and if you are keeping up with that, you'll see the progress is like at extreme fast paced. And there we have seen a substantial number of open source models which have also come out, and we're going to talk about a little bit of that. We will also talk about the risk associated with these video generation models and how to mitigate those. There is this paper that made a lot of noise last week by claiming that they can pretty much replicate the DeepSeek reasoning process or DeepSeek R1's reasoning process very, very cheaply. In fact, they said that they can do it, in fact, 1/10 of the budget of what DeepSeek claimed. But notwithstanding all those different models that DeepSeek came up with. So the total budget, 5 million or 10 million, whatever DeepSeek had, it's not just for the R1, it's also for the V3 model that they came out and the DeepSeek MOE that they came out. Main claim is that they can generate those DeepSeek reasoning processes using a very specific fine-tuning by extracting the chain of thought process of the models themselves. So let me elaborate. They elicited the chain of thought reasoning process that DeepSeek does, like, and DeepSeek shows that chain of thought reasoning, and people's like, oh, it's doing the reasoning. In fact, GPT models also do the chain of thought reasoning. It just didn't used to show them. Now, GPT OpenAI has actually added that step of showing the reasoning process so that people can see that it's happening and people believe, oh, that model is also good. Seeing is believing. Researchers are saying that they can replicate that reasoning process and improve the reasoning process at fraction of the cost. And this is how they said they did it. So the main idea is that you first ask the LLM a question. Now the LLM responds, and you also make sure the LLM responds with its chain of thought reasoning process. So it makes sure that the chain of thought is visible, just like DeepSeek shows its chain of thought. make sure that your reasoning large language model shows the reasoning steps that it is performing before giving the final answer. And then take those reasoning steps, and some of them might be inaccurate, some of them might be wrong, and make sure you label them correctly. And then feed it back into the model and fine tune the model. So here's how this works. Let's say the reasoning process is extracted. Let's say I asked a simple question: how many R's are in Raspberry? Okay, this is a question famously gotten wrong by older GPT models. There are 3 R's in Raspberry, and the older GPT model used to answer 2. There was an issue with their reasoning steps. So what happens when we ask this question is that the model will start answering. For example, the model answers like this. This is the chain of thought process of the model. Let's say the model responds as, let's break down the process of counting the letter R in the word raspberry. First letter is R, so count 1. Second letter A, okay, so the count still remains 1. Then it goes forward and then goes 6th letter E, not an R, count remains 1, and it goes forward, and at some point it makes a mistake, but it doesn't catch the mistake and gives the final answer 2. Newer ones have eliminated that step because they do a self-verification process. So what the authors are saying that now we can implement the self-verification process, take this chain of thought reasoning, okay, and let's say there was a mistake and it fixes the mistake. Sometimes it doesn't fix the mistake. Take all the correct answer and the wrong answer and label them correctly, and create your training data set out of those chain of thought responses. This is the beautiful part, and this is the impactful part. Create a training data set out of the reasoning output, not the final response of the large language model, but the reasoning steps. Extract the reasoning steps and create a data set out of those reasoning steps. So every time we ask a question, it will think for a little, extract those thinking process and label is correct or incorrect. Maybe the reasoning was incorrect, label is incorrect, and then use that to fine tune the model, right? So, or fine tune a thin layer of the model. These people actually have fine tuned the entire model. So you can fine tune an entire model, just make sure the model is small enough. And they are saying that we can do this as fraction of the cost that DeepSeek has used and get the same accuracy of the reasoning process. And this is important. What they're saying is that fraction of the cost means that they have to train a much smaller model. DeepSeek is a 641 billion model. At least the reasoning R1 model is a large model. It's a mixture of expert large language model. And in order to fine tune that model, it takes thousands and thousands of GPU clusters. But these researchers are saying that we can do it much cheaper for a smaller model and still achieve the same accuracy. What the researchers are saying is that they can take a 32 billion model, not the 641 billion DeepSeek model, not the 1.2 trillion GPT model, a 32 billion model, and fine tune it enough that its accuracy in math and other difficult question and answering problem sets, it reaches almost close to those top of the line models like GPT-4o and Gemini. These researchers are saying that they can achieve the same level of accuracy as Qwen 32 billion Instruct or O1 Mini or Gemini 2 with this 32 billion fine-tuned model. So that's amazing. This is one of the best things that could have happened, and this can be replicated very easily, and they release their code base, so which means people can replicate their results very easily. And I looked at the code base. It's very simple to replicate. You just need a powerful GPU to replicate the results, and that's why this result is so fascinating, that they have finally captured the essence of how to improve the reasoning process of these reasoning models. It just boils down to fine-tuning the reasoning steps, which is kind of a no-brainer. And in fact, they can reach almost as good as accuracy and precision as those top-of-the-line large language models, like literally large mixture of expert 600 or 1 trillion models. And that's an amazing feat to achieve. 32 billion model can achieve almost the same level of precision, or close to the same level of precision as 1.2 trillion model, and that's mind-boggling. One thing I'll just mention in passing, that they implemented something known as budget forcing, where they force the model which is overthinking to stop thinking, and it forces the model which is underthinking to think a little bit more. So if the model keeps thinking for a really long time without really achieving a final answer, then it will truncate that thought process, or In other words, if the model is not thinking at all, if it stops prematurely, then it will restart the thinking process to achieve the standard amount of thinking that it requires. So this is what they are calling budget forcing. They're budgeting some like 10 or 5 or 10 sentences of reasoning. If the model doesn't achieve that, underachieves or overachieves, then it will force the model to budget for that amount of reasoning process or thinking process, and that's a substantial step forward. So let's look at the new other innovations that are coming up in addition to this breakthrough. Another innovation that is gaining popularity is mixture of agents, and this is not something new. This is an old idea, not very old. It's only 6 or 8 months old, and sometime in June of 2024 researchers came up with the idea. Instead of using mixture of expert, where you use multiple large language model and mix them layer by layer, which is a very time consuming, laborious and difficult process. And also not only that, the mixture of expert, like if you take like 3 llama models and mix them, it's like, imagine that like 370 billion models, 3 times 70, around 200 billion model. It'll be huge. I mean, no consumer grade GPU can handle that size model. It's just impossible for consumers to leverage. And although some people did say, some enterprise users have said the mixture of expert models outperform than consumer grade models. But that's an aside, but that doesn't solve the main problem, which is the mixture of expert have a size issue. So now the one way around this is using this mixture of experts, where we do not use those large language models simultaneously or merge them together to make a massive model, but instead use them at inference time separately. So let's say this is a very crude version of how this was implemented, but it kind of gets the essence of how it's done. Let's say we are using 3 models. Let's say we have Llama 3, 3.2 would be better, multimodal. Let's say we have Qwen, and let's say we have DeepSeek R1. You might have noticed that we have used all open source models. Now we have used these 3 open source models, and then we ask it a very complicated question. Let's say, what is a black hole entropy, and describe how to calculate the black hole entropy of a 5-dimensional black hole. This is my standard go-to a difficult question that I'll have to ask large language models in order to evaluate their technical expertise. So let's say we ask these questions. OpenAI's GPT-4 usually 4o can answer this, but let's see these smaller models. Let's say these are Llama 3.2, 70 billion model. We usually might make mistakes. Qwen 32 billion will definitely make mistakes, and then DeepSeek R1 will not make that many mistakes, but it will have, the answer will not be sufficient. So what we do, what the mixture of agents is suggesting, take the answers from each of these LLMs, mix them together, and create some kind of an aggregation. Paradigm they are proposing is that there are 2 kinds of contributions. You can have proposers, so you can use 2 large language models like Llama, and let's say you can also use Qwen to propose an answer. And then you have aggregators. We can have, for example, the DeepSeek to aggregate the answers from Llama 3.2 to 70 billion. So some models are very good aggregators and some models are very good proposers, but their answers might not be that good. So for example, the answer from Qwen might be black hole entropy is similar to a thermodynamic concept, and it stops there. It's a proposal. It nudges the answer in the right direction, but doesn't give the final answer. So we take that answer, then feed it back to a better LLM, for example, Llama 3.2, and then aggregate the results. So that's a great idea. So it's like a chain, it's a feedback loop. Get answers like directions from smaller models, which might have seen the concept, but doesn't know the exact final answer. So it might give the right direction, but not give you the final answer. So it's like asking a very specific question to someone randomly at a university. Is like, hey, do you know where is the chemistry building or where is the physics building? They might know that, not know the answer, but they can point you to the information office, and then someone from the information office can give you the right answer. So the idea is similarly exactly the same. You have some proposers which can propose some kind of a correct answer, a general direction in which to go, and then the aggregators will take all those proposals and find the correct path to go. You can see the similarities between this and those chain of thought reasoning, tree of thought process, where we traverse a tree of thoughts to go in the right direction and slowly get nudged towards the right answer. Gained some traction there, but it didn't take off very much, and mostly because, as you can imagine, multiple large language models is used. So in order to use this, On a consumer grade GPUs, what do we need to do? We need to load a model. Let's say Llama 3.2 is loaded, answer is retrieved, answer is stored, then the model needs to be offloaded, then the next model, let's say DeepSeek 14 billion model needs to be loaded, then the information needs to be retrieved again from this model, stored again in the cache, and then the next model. So this, as you can imagine, this onloading, offloading will take a really long time. In fact, chain of thought process or any kind of reasoning process, self-refined, self-verification will give a better accurate answer much faster. In fact, if it's augmented by search, so any kind of RAG method, which is augmented by reasoning and search capabilities, will give an answer much faster. So this method didn't really catch on or get traction. In a very recent proposal, some researchers from Princeton University suggested, hold on, why don't we do this mixture of expert, but instead of using multiple large language models, just use one. Then we don't have to do continuous onloading and offloading of the large language model. We can use just one large language model to generate the answers. Then we can shift through the answers. So essentially, this is essentially like the tree of thoughts. Like you get like 3 or 4 different directions, then you aggregate all those directions and choose the best one. Now this is slightly different, and they explain what the main difference is. So what they do is that they use the same model to generate a few different answers, because every time you use a large language model, it is an auto-regressive model. So it will generate a slightly different answer. You take those different answers and then aggregate them. So the same model is now acting as a proposer and an aggregator. So now you aggregate and follow the same process as we did before with the initial mixture of experts with different large language model. Now the question they're asking, and they thought they should ask, and I agree, is that does the benefit of the mixture of agents stem from cross-model diversity, which means just by eliminating all those different models and replacing by a single large language model, does it really help? Or was the real advantage or high accuracy in the reasoning process was coming from the model diversity? Imagine this, if we ask the same question, let's say technical question, to 5 different professors, each will give slightly different answers, but their aggregated answer would be so much better than each individual answers. This is like a mixture of expert things, but this is called mixture of agents. Now, that question is very relevant. Like, is the benefit stemming from the diversity of the different large language models that are being used? And can we build a strong mixture of agents using in-model diversity? By in-model diversity, they mean that we're going to use the same large language model, but the diversity is going to come from the diversity in responses with slight difference in those responses that we achieve. And they answer both the questions very beautifully. What they show is that the model diversity is not the main contributing factor to the improvement in the quality of the responses. Let me repeat, it's model diversity that was used for the mixture of agents. Those using different models is not improving the final results. Is the diversity itself is impossible. And we know this from if we have looked at random forest classifiers. Why are those models with such large variance so stable in their responses, perform so much better? Why does XGBoost perform so much better than those simple decision trees? And the reason is simple, because substantial amount of model diversity, even though it has a large variance, produces a mean result. The mean itself has very low variance, and this is a very simple statistical results. And the same result here, we have diversity in responses, and the diversity need not come from different language models. It can come from the diversity of responses from a single large language model. They essentially prove that self-MOA, or self-directed mixture of agents using the same large language model to create diverse responses, and then choosing from those diverse responses is enough. Now this is in a very nascent stage, so I don't recommend using this right away, but this is a very interesting paradigm we should look into, and this might evolve into something massive in this year of 2025. Another paradigm that I really liked, and I quickly hinted that during the introduction, is the chain of associated thought. And this is a very involved framework, so I'm not going to go too much into it. But if you're familiar with chain of thought, this is similar, but they use something known as the Monte Carlo tree search to it. So essentially the idea is simple. This is similar to the tree search or chain of tree thoughts, but slightly different. And the Monte Carlo search tree has a very specific mathematically rigorous treatment. So the chain of associated thought is, as it says, that it starts with a chain of thought prompting. So it has some chain of thought and finds something similar around it, any kind of associated thought, those thoughts also get explored, just like you do a tree search, and then it creates that tree of thoughts, and each node in the tree gets some kind of a score. So let's say we ask a question that discuss the economic impacts of AI, focusing on leading countries in US, etc. Then it goes into role of AI in international competition. Then another node might go into role of AI, role of a regulatory environment, and then another node might go into European Union, another node might go into US's involvement and implications of AI in day-to-day life, and then each node will research each different avenue, just like human thought process. We think about something, then we have a few associated thoughts, then we explore those thoughts and we flesh it out. Just like the same thing, each thought process is followed in its entirety, and then each node is given some score according to its relevance. Then results from each node is weighted. So essentially the steps are very simple. You have some expand your thoughts and you perform those associations, evaluate each thought process, each chain of thought, and then bring them back together and combine them. So that's pretty much, but the whole paper is very technical, so I'm not going to go into that, but that's the essence of the chain of associated thought. If you're interested, I'll post a link, you can explore more. So the next up, the one we want to discuss is SynRetriever. The paper is called SynRetriever: How to Train Your Retriever with Synthetic Data from Large Language Models. So essentially what they're doing, they're distilling the knowledge from the large language model and putting a small layer, a thin layer of trained model on top of the large language model, so you can use any large language model. So this is an evaluation of the self-refine or the self-verification framework, and we discussed self-refine and self-verification in an earlier episode. I'm going to post a link as well, but if you want a quick answer, you can just ask ChatGPT or just look it up online. It's very simple. Self-refine is the LLM gives a response, then you use some kind of prompt engineering technique to feed the response back and ask it to refine further, evaluate the response and refine further. Essentially some form of reasoning process. The self-verification is the same, but it is search augmented. It says, was Albert Einstein a German physicist, or was he born in Germany, or was Mayor Bloomberg, was he born in New York? So these are verifiable facts. So Mayor Bloomberg was not born in New York. So self-verification will go online and search and gets the response. So initial LLM response would be augmented with the search response, and it will be self-refined. So those paradigms already exist and been augmented by those reasoning process that you see in the latest iterations of DeepSeek R1. Now, where does this retrieval, SynRetriever, comes in? As I said in the introduction, SynRetriever lies somewhere between that prompt engineering techniques of self-refine and self-verification and refine and react that we discussed earlier, and a fully fine-tuned large language model that you see in DeepSeek R1 or the OpenAI models that are supervised, fine-tuned through reinforcement learning with human feedback. Now, what it does, it takes regular large language model responses, but instead of using prompt engineering, they train a thin layer of another model which has a reward function. So it gets the responses from the large language model, it performs some form of self-verification, and then collects all the information and stores it. Okay, so now then there is an alignment step that's done on the model. What it does, it then uses all those to go to the next stage, and the next stage is essentially alignment with the LLM. So it takes all those responses and creates a data set, and it uses that data set that it's created using the self-verification process of the large language model to train itself. What happens is when the model is fully trained, it sits between the large language model and the user. User asks the question, it flows through the retriever, SynRetriever to the LLM. LLM gives a response, and SynRetriever starts this feedback loop from its based on its prior training. So if it sees a large language model response which it thinks is not very good, then it sends it back till it gets the response it thinks is up to par. So it iterates the process. So essentially, when we used to chat with ChatGPT like a year back, and we didn't get the right answer, we have to keep asking it again and again from different angles. So SynRetriever essentially is automating that step. It's reducing our workload. So essentially taking those things that we do normally, where we prod and ask and coax the LLM response in the format we want, it is actually eliminating all the task and incorporating all those human alignment, task into one single layer of aligned stage. probably have seen these videos of Einstein talking, actually AI generated. And this is a new model that is published by ByteDance, which is the parent company of TikTok. And they have released this state-of-the-art text-to-video generation model. And this will take an entire episode to talk about this. So we're going to quickly mention this. Text-to-video generation has come a long way from with those 5-second videos that were generated by Kling AI, which was not very good and not very prompt following, to fully prompt following. In fact, we can use start and end frames to create frame-to-frame interpolations with just text prompting. And this has come a long way, and this is the state-of-the-art model. They published their entire architecture and how they do it, but it is possible that some of our videos might be used for training these video models. I'm not sure. It might happen because all these social media influencers or content creators, they are uploading the videos, but also massively tagging and annotating these videos with an extreme detail in order to have the algorithm pick these videos up. It's a stiff competition out there, and all the content creators, and myself included, tag the videos and annotate the videos heavily for the algorithm to search optimally. And the result is that we have heavily annotated videos which would cost billions of dollars for human annotators to produce, to annotate the videos manually. Now these are already annotated, and if someone has access to these rich troves of data, annotated video, they can just use it to train their text to video or image to video models very easily at fraction of the cost what would have cost to manually annotate the videos. So this model is so detailed that it will take an entire episode just to talk about the architecture. The architecture is very interesting. It follows the diffusion transformer model, and if you remember from our earlier episodes, we talked about the diffusion transformer. Essentially, it's merging the diffusion process along with the transformer model. So we get a diffusion transformer model which is highly efficient in generating images and now videos. And we're going to talk about this more in a future episode. That's all for today. Thanks for listening. Talk to you next week. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.